Welcome to Night Lesson. Relax and learn along the way. Beyond the Big Bang, alternative theories on the origin of the universe. Please, make yourself comfortable. Close your eyes if you wish. Tonight, we embark on a journey to the frontiers of our knowledge, to the most fundamental questions human beings can ask. How did the universe come to be? Did it have a beginning? And if so, what came before? For decades, we believed we knew the answer. The Big Bang, approximately 13.8 billion years ago, marks the beginning of everything: space, time, matter, and energy. It is a theory that has shaped generations of scientists, a theory written in textbooks and considered settled fact. But in recent years, this certainty has begun to crumble. New instruments like the James Webb Space Telescope are sending images back to Earth that do not match our expectations. Galaxies that are too old, structures that appear too perfectly ordered, stars that existed shortly after the supposed Big Bang. Even though the theory says this should be impossible, some of the brightest minds in physics are asking, have we been mistaken? Not entirely, perhaps, but maybe in important details. Perhaps the story of the universe is more complex, more surprising, more fascinating than we thought. Tonight, we will explore alternative theories. Some come from Nobel laureates, others from courageous scientific outsiders. Some sound like science fiction, but are mathematically sound. Others have already been disproven, but teach us important lessons. This is not a journey to discredit science. On the contrary, it is a celebration of science, of its self-correcting nature, its willingness to question even its most fundamental assumptions. For that is what distinguishes science from dogma: the willingness to say, perhaps we have missed something. Let us begin. To understand the alternatives, we must first understand the standard theory. The Big Bang is not simply an explosion in space, but the explosion of space itself. 13.8 billion years ago, the entire universe was concentrated in an infinitely small, infinitely dense point that physicists call a singularity. In this point, there was no time, no direction, no distance. All the laws of nature, as we know them, break down. Then, in a moment shorter than the briefest measurable instant, the universe began to expand. Not into something, but space itself stretched, carrying matter and energy along with it. In the first fractions of a second, the universe was unimaginably hot and dense. Quarks and gluons, the building blocks of matter, were formed. After a few minutes, it cooled enough for the first atomic nuclei to form, mainly hydrogen and helium. For 380,000 years, the universe was opaque, a hot plasma of matter and radiation. Then, at a temperature of about 3,000 degrees Celsius, the first neutral atoms became stable. The universe became transparent. We can still measure the light from this era today as the cosmic background radiation, a faint glow in all directions of the sky. This theory explains many things very well. It explains why the universe is expanding, an observation made by Edwin Hubble in 1929. It explains the composition of the universe, about 75% hydrogen and 25% helium. It explains the cosmic background radiation, which was discovered by chance in 1964 and earned the Big Bang theorists the Nobel Prize. But there are problems. Small cracks in the elegant edifice of the theory. The horizon problem. The universe looks the same in all directions, even though these regions could never have been in contact. How can they have the same temperature? The flatness problem. The universe is geometrically remarkably flat, meaning parallel lines will never converge. But this flatness is extremely unstable. Even the slightest deviation should have led to a curved universe. The monopole problem. Theoretical physics predicts that magnetic monopoles, particles with only one magnetic pole, should have been created in large numbers shortly after the Big Bang. We have never found one. And then there are the latest observations. The James Webb Telescope shows us galaxies that, only a few 100 million years after the Big Bang, already appear to be fully developed. Red giants, massive stars that take billions of years to form. How is this possible? Some physicists say the Big Bang theory is correct in its core, but it needs refinement. Others say perhaps we need to think more radically. Breathe in deeply. Breathe out. We are now opening a door to worlds beyond the Big Bang. Imagine the universe had no beginning, not in the true sense. Instead, it undergoes endless cycles of expansion and contraction, like the inhaling and exhaling of a cosmic being. The Big Bang was not the beginning, but a transition, a big bounce, a return from a previous phase. This idea is ancient, found in Hindu and Buddhist cosmologies, where the universe exists in cycles of creation and destruction, each cycle lasting billions of years. But today, there are mathematical models that translate this poetic vision into precise equations. Nobel laureate Roger Penrose, one of the pioneers of black hole physics, proposes a model he calls conformal cyclical cosmology. In his picture, our universe does not end in a cold, dark death, when all the stars have burned out and all the black holes have evaporated. Instead, when only photons, particles of light, remain, space and time lose their meaning. Photons have no mass, they experience no time. In a universe without mass, there are no clocks, no rulers. In this state, says Penrose, the end of the old universe could be identical to the beginning of a new one. What we call the Big Bang would be the threshold between two eons, two infinitely long epochs. And there was not just one Big Bang, but countless, in a chain stretching backward and forward into infinity. Is there evidence? Penrose and his team claim to find traces in the cosmic background radiation, concentric rings of slightly elevated temperature, which could come from collisions of supermassive black holes in the previous eon. Other scientists are skeptical, explaining these patterns as statistical noise. Another approach comes from Paul Steinhardt and Neil Turok. Their ekpyrotic universe is based on string theory, the idea that the fundamental building blocks of reality are not particles, but tiny vibrating strings. In their model, two parallel universes exist, separated by a higher dimension, as if they were two sheets of paper almost, but not quite, touching. Every few trillion years, these membranes collide. The collision releases enormous energy, creating matter and radiation, appearing to us as a Big Bang. Then the membranes drift apart, the universe expands, cools, and empties, until the next collision, and so on, forever. This theory elegantly solves some of the problems of the standard Big Bang. The horizon problem disappears because the universe had time to even out before the bang. The flatness is natural because the slow approach of the membranes smooths the universe. But here too, there are doubts. String theory itself isn't proven. Critics say it is too early to build theories on something that is itself still speculative. But the idea is deeply satisfying. A universe with no beginning, no end, only eternal change. Perhaps we are just one breath in a cosmic cycle that never ends. The idea of a cyclical universe has fascinated not only physicists but also artists. The 2006 film, The Fountain by Darren Aronofsky, tells a poetic story about cyclical time, rebirth, and the connection between death and new beginnings. Although the film is not based on Penrose's scientific theory, it captures the emotional depth of the idea that endings are beginnings, that nothing is truly lost, only transformed. In the 1940s, when the Big Bang theory was still young and controversial, three British astronomers proposed a radical alternative. The universe had no beginning. It has always existed and will always exist. It is expanding, yes, but it is not thinning out, because new matter is constantly being created from nothing. Fred Hoyle, Hermann Bondi, and Thomas Gold called this the steady-state theory. The name Big Bang, by the way, comes from Hoyle himself, who used it mockingly to ridicule the competing theory. Ironically, the name stuck. In Hoyle's universe, hydrogen atoms are constantly appearing in empty space, about 1 atom per cubic kilometer per year. A tiny amount, far too small to be directly measured, but sufficient over cosmic timescales to keep the density of matter constant as space expands. Where does this matter come from? Hoyle speculated about a creation field, a kind of reverse gravity that generates matter from the energy of expanding space. The details remained vague, but the elegance was captivating. An eternal, unchanging universe, without a beginning, without an end, without the metaphysical complications of a creation event. For a while, it was a neck-and-neck race between the Big Bang and the steady state. Both explained the expansion. Both had mathematical models. The decision would have to come from observation. Then, in 1964, Arno Penzias and Robert Wilson made an accidental discovery. They were working with a large radio antenna, trying to eliminate a persistent source of noise. No matter what they did, a uniform background signal remained, coming from all directions at a temperature of about minus 270 degrees Celsius. It was the cosmic background radiation, the afterglow of the Big Bang, just as the Big Bang theorists had predicted. For the steady-state theory, this was fatal. There was no explanation for this ubiquitous relic in a universe without a beginning. Hoyle did not give up. He tried to explain the background radiation with dust in distant galaxies, but the explanations became increasingly complicated, increasingly unlikely. Eventually, the majority of scientists accepted the Big Bang. Why do I tell this story? Because it shows how science works. Hoyle was wrong, but he was wrong in a productive way. His challenge forced the Big Bang theorists to refine their theory, to make better predictions, to search for decisive evidence. And perhaps Hoyle was right on one point. The idea that something can come from nothing is not absurd. Modern quantum physics shows that particles constantly emerge from the vacuum and then vanish. The universe itself could be a quantum fluctuation, a gigantic particle that sprang from nothing. In that sense, the difference between the Big Bang and the steady state is perhaps smaller than it seems. Both are theories of creation from nothing, just on different timescales. Close your eyes. Imagine that in this moment, as you hear these words, infinitely many other versions of you exist. In one universe, you stayed awake. In another, you chose a different video. In another, you were never born because your parents never met. Welcome to the multiverse theory, perhaps the boldest idea in modern cosmology. The idea has several origins. One comes from quantum mechanics, the theory of the smallest particles. In the standard interpretation, the wave function of a particle collapses when we measure it, and only one of many possibilities becomes real. But in 1957, Hugh Everett proposed, what if the wave function doesn't collapse at all? What if all possibilities become real, just in different, parallel universes? Every time a quantum event could have multiple outcomes, the universe splits. The number of universes grows exponentially every second, every nanosecond. An infinite tree of realities, branching and branching. It sounds absurd, yet mathematically, it is the simplest interpretation of quantum mechanics. No additional assumptions, no collapse mechanisms. Just the Schrödinger equation, with no additions. Another approach comes from the theory of inflation. In the 1980s, physicists like Alan Guth proposed that the early universe went through a phase of exponential expansion called inflation. In a fraction of a second, a tiny patch of space inflated to the size of a galaxy or larger. Inflation solves many problems of the standard Big Bang, but it has a strange property. Once it starts, it never completely stops. In most regions, inflation ends, space cools, and galaxies and stars form. But in other regions, inflation continues, creating more space. And in that space, new regions arise where inflation ends, and new ones where it continues. The result is eternal inflation, an infinite foam of bubble universes, each bubble a separate universe with its own laws of nature, its own constants. In some universes, gravity is stronger and stars burn out faster. In others, there is no light, only darkness and cold matter. In our universe, the constants are just right for life. Why? Not because the universe was made for us, but because we can only exist in a universe that permits life. This is the anthropic principle. We observe what we observe because otherwise, we would not be here to observe it. Critics say the multiverse is not science because it is not testable. If other universes are forever unreachable, how can we prove they exist? Proponents respond, we can look for indirect evidence. Perhaps traces of collisions between universes in the cosmic background radiation. Perhaps mathematical consistency and the predictive power of the theory. Perhaps the multiverse is the simplest explanation for the observed facts. And perhaps the idea is not as strange as it seems. We once believed the Earth was the center of the universe. Then we discovered that the Earth is a planet, one of many. Then, that the Sun is a star, one of hundreds of billions in our galaxy. Then, that our galaxy is one of hundreds of billions. Each time, we thought we were special. Each time, the universe taught us humility. Perhaps our universe is just one bubble in an infinite ocean. Perhaps this humility is the final lesson. Imagine our entire universe, with all its galaxies, stars, planets, with you and me and every atom that has ever existed, is located inside a black hole. Not trapped, not crushed, but spacious, expanding, alive. This bizarre idea comes from physicist Nikodem Poplawski of the University of New Haven. His theory is based on a fascinating property of black holes. We do not know what happens beyond the event horizon. According to Einstein's general theory of relativity, all matter that falls into a black hole collapses into a singularity, a point of infinite density. But singularities are problematic. Physicists do not like infinities. They suggest that the theory is breaking down. Poplawski uses torsion, a property found in extended versions of relativity theory. Torsion prevents matter from collapsing to a single point. Instead, it bounces, like a ball hitting a floor, creating a new region of space and time. From the outside, it looks like a normal black hole. But from the inside, from the perspective of the matter falling in, it looks like a Big Bang. The collapse from the outside is the expansion from the inside. This means every black hole in our universe could contain an entire universe with its own galaxies, stars, perhaps life. In our universe, perhaps we are inside a black hole that exists in another, larger universe. It is an idea of breathtaking elegance. It solves the singularity problem. It explains why we cannot directly observe the Big Bang. It is hidden behind an event horizon. It offers a natural explanation for the expansion as matter rebounds from the center and flows outward. And it has a philosophical dimension. If every black hole is a universe, and every universe contains black holes, then we have a nested hierarchy of universes, universes within universes, to infinity. Critics point out that the theory is difficult to test. We cannot look inside a black hole to see if a universe is there. And from the inside, we cannot look out to confirm that we are in one. But perhaps there are indirect tests. The theory makes predictions about the rotation of black holes, about the polarization of light from the early universe, about the distribution of matter. With more precise observations, we could test these predictions. Until then, it remains a fascinating speculation. But isn't it comforting to think that even the emptiest, darkest, most terrifying thing we know, a black hole, could be internally alive, full of light and life? Perhaps the universe is not just more wondrous than we imagine. Perhaps it is more wondrous than we can imagine. There is a war in physics, a quiet, polite, but fundamental war between two great theories that shape our understanding of reality. On one side is the general theory of relativity, Einstein's masterpiece, the theory of gravity, of space-time, of large things, planets, stars, galaxies, the universe as a whole. On the other side is quantum mechanics, the theory of the smallest things, atoms, particles, waves, uncertainty. Both theories are extremely successful, the best tested theories in history. But they speak different languages, are based on different principles, and when you try to combine them, you get nonsense, infinities, contradictions. The problem becomes acute when we think about the Big Bang. The singularity, the point of infinite density, is a place where both gravity and quantum effects are extremely important. To understand it, we need a theory of quantum gravity, a unification of the two great theories. There are several candidates. We have already mentioned string theory. Another, more radical idea is loop quantum gravity. In this theory, developed by Lee Smolin, Carlo Rovelli, and others, space and time are not continuous, not smooth, but granular, discrete, composed of tiny building blocks, quanta of space and time. Imagine zooming further and further into space. First, you see atoms, then atomic nuclei, then quarks. But you don't stop zooming. You go further until you reach the Planck scale, 10 to the power of minus 35 meters, a distance so small that it is beyond human intuition. At this scale, says loop theory, space is a network of loops and nodes, a fabric, a foam. There are no smaller distances because there is no space between the loops. Space is the loops. And time. Time is not fundamental. It emerges from the fabric, just as temperature emerges from the motion of atoms. At the most fundamental level, there is no time, no change, only a static pattern of relationships between loops. What does this mean for the Big Bang? In standard relativity, the singularity is the end of time, a point where physics ceases to exist. But in loop quantum gravity, there is no singularity. If space is made of discrete building blocks, it cannot collapse to a point. There is a minimum size, a quantum limit. Instead, we get a big bounce, as in the cyclical universe. The universe collapses, but not completely. At an extreme but finite density, it bounces back, expanding again. The Big Bang is the rebound phase. The theory is mathematically sound, but experimentally difficult to test. The effects of quantum gravity are so small that we would need huge particle accelerators, larger than the solar system, to measure them directly. But perhaps there are indirect ways. Tiny distortions in the cosmic background, irregularities in the propagation of light over cosmic distances, differences in the speed of photons of different energies. And philosophically, the idea is profound. If time is not fundamental, then there is no before the Big Bang, because before is a temporal statement. The question, what was before the Big Bang, is meaningless, like asking, what is north of the North Pole? Perhaps this is the ultimate answer. Not that we don't know, but that the question itself is based on false assumptions. Perhaps the universe is not in time, but time is in the universe, an aspect, a perspective, an illusion. Breathe in deeply. Breathe out. We now turn to a theory that stands at the edge of mainstream science, controversial, rejected by most cosmologists, but with a small, passionate following. Plasma cosmology claims that electric currents and magnetic fields, not gravity, are the dominant forces in the universe. Plasma, ionized gas, makes up 99% of the visible matter in the universe. And plasma behaves differently from normal matter. It can conduct currents, generate fields, and organize itself over vast distances. Hannes Alfvén, a Swedish physicist and Nobel laureate, was one of the pioneers. He studied plasma physics as applied to the solar system, to stars. In the 1960s and 70s, he proposed extending these principles to the entire universe. In his picture, there was no Big Bang. The universe is ancient, perhaps infinitely old. What we interpret as expansion is a local motion, not a global property of space. The cosmic background radiation does not come from the Big Bang, but from radiation from distant plasma clouds. Galaxies do not form primarily through gravity, but through electric currents flowing through intergalactic space, forming filaments and gathering matter. We actually see these filaments, the large-scale structure of the universe, a cosmic web. The theory is attractive because plasma is so common and because electric forces are much stronger than gravity. On small scales, in laboratories, and in the solar system, plasma physics works brilliantly. But on cosmic scales, most cosmologists say no. The cosmic background radiation is too uniform, too precise, to come from chaotic plasma effects. The expansion of the universe is consistent in all directions, not local. The synthesis of light elements fits perfectly with the Big Bang theory, not with an electric cosmology. Plasma cosmologists respond. Mainstream science ignores 99% of matter, focusing too much on gravity. They point to anomalies, observations that do not fit the standard model. But here is the problem. Every theory has anomalies. The question is which theory explains the most observations with the fewest assumptions. And by that criterion, the Big Bang wins. Why do I tell this story? Not to promote plasma cosmology, but to show that science is a process. Minority opinions are important. They keep the majority honest, forcing them to justify their assumptions. Alfvén was wrong about cosmology, but he was right about plasma physics. His work on magnetic fields in the solar system was groundbreaking, earning him the Nobel Prize. Perhaps the lesson is, even brilliant minds can be wrong when they extend their expertise into unknown territory. And conversely, even if mainstream science is right, it should remain open, ready to change its mind when new evidence emerges. Dogma is the death of science. What if everything you know is an illusion? Not in a spiritual sense, but literally. What if the universe is a computer simulation programmed by an advanced civilization, and you, me, the stars, the galaxies, the Big Bang, are all just code? This sounds like science fiction. Yet some of the brightest philosophers and physicists take this idea seriously. Nick Bostrom, a philosopher at the University of Oxford, formulated the simulation argument in 2003. His logic is elegant and unsettling. He proposes that one of three statements must be true. 1. Civilizations almost never reach the stage where they have the technological ability to create realistic simulations of their ancestors. 2. Civilizations that do reach this capability have almost no interest in creating such simulations. 3. We are almost certainly living in a simulation. Why? If civilizations survive and are interested, they would likely create many simulations. Perhaps thousands, millions. For every real universe, there would be countless simulated ones. Statistically, it would be more likely that we are in a simulated one. The argument rests on assumptions. Perhaps it is impossible to simulate consciousness. Perhaps there are ethical laws that forbid it. Perhaps advanced civilizations destroy themselves before they get that far. But suppose it is possible. How could we test it? Some physicists suggest looking for glitches, small irregularities that might indicate limited computing power. For patterns that are too perfect, too symmetrical, like pixel errors in a video game. Others suggest that certain physical constants, like the speed of light or the Planck constant, could be clues to a discrete, digital foundation. The universe seems to have a resolution limit, the Planck scale, beyond which physics breaks down. Is that a bug or a feature? And then there is quantum mechanics itself. In a simulation, you wouldn't render every detail. That would be too costly. You would only render what is being observed. Just as quantum mechanics works, particles are in an indeterminate state until they are measured. Is that a coincidence? Some physicists, like NASA scientist Rich Terriel, say, within a century, we ourselves will be able to create realistic simulations. If we can do it, why not others who are millions of years older? Others, like Sabine Hassenfelder, are skeptical. She says the simulation theory is not scientific because it is not falsifiable. Any observation can be explained with, that's how the simulation is programmed. Philosophically, The idea is ancient. Plato's allegory of the cave. Descartes, evil demon. Buddhism teaches that the world is Maya, illusion. Only the technological language is new. And perhaps it doesn't matter. If the simulation is perfect, if there is no way to escape or to know the difference, then it is, for all practical purposes, real. Pain feels like pain, joy like joy, love like love. But the question is humbling. It reminds us that even our deepest certainties can be questioned. Perhaps that is the ultimate lesson. Stay humble. Stay open. We know less than we think. It is an irony that a telescope designed to confirm the Big Bang Theory has instead raised questions that challenge it. The James Webb Space Telescope, launched in December 2021, is the most powerful telescope ever built. With a 6.5-meter mirror and infrared sensors that can see through dust, it looks deeper into space and time than ever before. Astronomers expected to see early galaxies, formless, small, chaotic. What they saw surprised them. Galaxies, only 300 to 500 million years after the Big Bang, that are already large, structured, mature. Spiral arms, red giants, massive stars. According to the standard theory, this should be impossible. Stars take time to form. Small fluctuations in the distribution of matter grow slowly through gravity. The first stars should be small, short-lived, without heavy elements. Only after several generations should galaxies like ours emerge. But James Webb shows galaxies that look as if they were billions of years old, not hundreds of millions. Some astronomers speak of a crisis in cosmology. Is the Big Bang Theory wrong? Most scientists say no, but perhaps it needs adjustments. Perhaps star formation in the early universe was more efficient than we thought. Perhaps there was more dark matter, pulling galaxies together faster. Perhaps our models of stellar evolution are incomplete. Or maybe something more fundamental is wrong. Some physicists suggest that dark energy, the mysterious force that accelerates the expansion of the universe, was different in the past, or that the gravitational constant had a different value in the early universe. These are radical ideas. They would mean that the laws of nature are not constant, that they change over time. This would complicate many things, but it is not out of the question. Other observations add further puzzles. The Hubble constant, the rate of the universe's expansion, has different values depending on how we measure it. Measurements from the early universe, based on the cosmic background radiation, give one value. Measurements from the modern universe, based on supernovae and galaxies, give another. The difference is small, but significant, and no one knows why. This could be a sign that our models are incomplete, or it could be a measurement error, or it could be something new, exciting. This is the moment we live in. A moment of uncertainty, of open questions, of possibilities. It is uncomfortable not to know, but it is also exciting. Some see James Webb's discoveries as evidence for alternative theories, the cyclical universe, plasma cosmology, the black hole theory. Others say, be patient, collect more data, don't embrace new theories hastily. The truth is, we don't know yet. And that's okay. Science is not a building of finished answers. It is a process, a journey. We stumble in the dark, with theories as flashlights. Sometimes they light the way, sometimes they lead us astray. But we learn. With every step, every mistake, every correction, we get closer. Breathe in, breathe out. We have reached the end of our journey. Or perhaps the beginning, because every answer opens new questions. What have we learned? That the Big Bang Theory, as dominant as it is not the final word. That alternatives exist, some plausible, some speculative, all fascinating. That science is alive, evolving, self-correcting. The cyclical universe reminds us that beginning and end may be illusions, that the universe breathes in eternal cycles, with no first breath and no last. The steady-state theory, though disproven, taught us that creation need not be confined to a single moment, that the universe can be born anew in every instant. The multiverse theory humbles us, showing that we may be just one bubble in an infinite ocean, insignificant in the grand scheme, but infinitely precious in the small. The black hole theory shows that even the darkest places can contain light, that complexity can be nested within complexity unto infinity. Quantum gravity teaches us that time may not be fundamental, that space is woven from loops, that the question of before may be meaningless. Plasma cosmology, though on the fringes, reminds us to stay open, to question assumptions, even when the majority agrees. The simulation theory, as bizarre as it sounds, shows that even our deepest certainties are hypotheses, open to doubt. And James Webb shows us that the universe still holds surprises, that we know less than we thought, that the journey is far from over. Perhaps this is the true beauty of science. Not that it has all the answers, but that it is willing to be wrong. That it rejoices when new data challenges old theories. That it embraces uncertainty, not as a weakness, but as an invitation. Dogma says, I know the truth. Science says, I seek the truth, and I am willing to change my mind when the evidence demands it. In this spirit, we conclude, not with certainty, but with wonder. The universe is grander, stranger, more wondrous than we can imagine. And that is a beautiful thing. Close your eyes, rest, and dream of universes beyond the Big Bang, of cycles without end, of bubbles and infinite foams, of black holes full of light, of time that does not exist, of simulations within simulations, of questions that lead to answers that lead to questions, forever. Good night. Sleep well. The universe is waiting.
That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.